Yeah, thank you very much, Camilla, for the introduction, and thanks for having me. And also thanks, Karen, for inviting me as well. I'm enjoying my trip so far, and I enjoy meeting people and things like that. So yeah, as the title says, we're talking about level sets. So weekly. And I'll say that this is actually joint work with one of my former PhD advisors, Mariana Chenier, and one of her current graduate students, Ikra Altal. And it's actually going to be a fairly simple talk today. It's something that I kind of thought of last year. The notion of regularity that I'll talk about is something that Mariana and I have been talking about or thinking about for the last 10 years. But the particular question just came up randomly last year at some point. I don't know where it can go or what I can do with it, if anything, or what it means, or if there are any questions or interesting questions at all, but I'm still trying to figure that out in some sense. So to some extent, I think this talk is a little bit of a fishing expedition. So we're talking about level sets. And I suppose you start with maybe the easiest example. You take some function. You assume it's C2. Okay, and then you can see, I suppose, just by Sar's theorem, that level sets to this function. Nice curves, right? Locally, just by the Blissen function theorem, right? Okay, so I happened upon at some point some paper looking at Lipschitz functions and things like this. Some paper of Alberti, Bianchini, and Kripa. This is from 2013, in which they were looking at level sets of Lipschitz functions. Okay, so. And I'll write it, let's say in general, let's say it's RK, in F Lipschitz. So, not everyone has the same definition of Lipschitz, so you always write down the definition, even though it's a very trivial thing. So, of course, I'm here to and so I'll write down part of a theorem that they have, but it's actually a fairly kind of simple part of the main theorem of their paper. Okay, so part of a theorem. That if you have F then or almost everything. Okay, rectifiable. is not a big deal here. This is just a covariate formula, essentially. You can prove this. The larger context of what they were dealing with was looking at maybe finer properties of level sets, in particular in the k=1 case. All right, they would like to say that that if you take k=1, then level sets almost everywhere have to be, if they're connected, if the level set is connected, it has to be parameterized by a Lipschitz curve. Okay, a closed Lipschitz curve, or it's a singleton. Right. All right. So this is as part of a larger larger characterization. Okay, so but this is the kind of the direction I want to go, and I want to essentially reduce the regularity of Lipschitzness and understand to what extent what one can say. Okay. And the reason that I ended up at this place or with this question, I think, if I remember correctly, at the beginning of last year, at some point, Camila was actually giving a talk in this fluids program at MSRI that no one actually went to in person, or some people did. But I always forget that it existed. But at some point, giving a talk, I think that about some joint work with you and Prouet and Colombo on continuity equations and transport equations. And I think I was very interested in this. I thought it was a really interesting talk. And so I did some looking around. I went down a rabbit hole and I found this paper by Alberti, Bianchini, and Kripa. And so, I was wondering, as I guess you typically do with analysis, if this is related to somehow showing that there exists solutions, let's say, to a differential equation, can you lower the regularity and show that you have some type of existence? Okay. And this was maybe a half-baked idea that I had, well, maybe if you had some lower regularity other than Lipschitz, then you could show something like an existence for a certain type of data, okay, for a continuity equation, or possibly a short time type of existence or something like this. Sure. But this is completely, I have no idea whether this can be done or not. Okay. There's a lot of problems, and you will see with the weaker definition of Lipschitzness that I give, that you don't have differentiability almost everywhere, which is what's necessary when you're relating this to the continuity equation. Okay, but regardless, let me try to give you an idea about what we start off with. So first, I'll just give the weaker notion of rectify or Lipschitzness that I'll and this is a scaled oscillation. So there's two things. There's lower scaled oscillation. There's upper scaled oscillation. And they look just like local Lipschitz notions, okay? So if you have a function, you want to say little l f of x, it's going to be 0 of soup x minus y star r, and then the upper scaled oscillation, the big lip, So the big lip is basically like a local Lipschitz constant. Okay, it's finite if and only if the local Lipschitz constant is finite. The small lip is a little bit less strong of a condition, and so I guess geometrically, what you would like to think of is that if you have a Lipschitz condition, at least near a point, then you have some type of geometrically, you have some type of cone that you can kind of envelop your function as and center at the point in question. The little f essentially says you have this kind of sequence of scales in which you can do this, okay? And you have no control over the sequence of scales. This is like something that happens a lot when you're talking about these. You may have some quantity that's derived from certain conditions, and you may have no control over the scales at which this quantity exists, or maybe you have some notion like doubling or something like this, which may be in certain situations nice for every scale, but in certain other situations maybe not nice for most scales. So a general question, of course, is to what extent can you recover any information about level sets or functions that satisfy maybe a small condition. Okay, at least it's bounded, let's say. And you can maybe even talk about, I suppose, like some type of Sobolev condition, integrability of this little f or a little L. But I would like to talk about just for boundedness. Okay. So a question. And let's say little L f is bounded except for some exceptional set.
Bounded pointwise, like never infinity.
Sorry?
You mean bounded pointwise?
Yeah, bounded pointwise, yeah. For all. Exceptional set. Continuous implies what about in particular, maybe one can show some level sets are fairly nice. We have rectifiability, or maybe one can show that on most level sets you have some nice rectifiable part, or somehow you can say that the non-rectifiable part is going to be small or insignificant. But this is the first question to start with. And so the next step is, of course, well, why would you expect anything? Why would you expect any type of regularity from this type of condition? And this is something that Mariana and I had looked at a while ago. So, here, 14 maybe. Some function r that's all accountable. There exists some such that it's positive and okay, so it's a weird statement in some sense, right? Because you have some positive measures of differentiability, but there's no description of what this looks like or anything like that. And the proof is by contradiction as well. So it's even worse than it looks. some sense. Okay, so but given this, okay, given this, what can one
And
expect?
when you say F is differentiable on E, you really mean
Differential
so
in the calculus sense, yeah.
but X is in E and the differentiability is in R in 0, 1 to D, not the differentiability of the restriction.
Yeah.
Okay.
Not the true.
So it's generally differentiable.
Yeah, generally.
Can I ask maybe an easy question for the people who do GMT, but if the upper L is bounded at every point, then what does that imply about the level sets? Is the big L?
I don't know. Or so sorry. So what is it?
If big LF,
What if big L?
if this is bounded, if this is fine at every point, then what does that imply?
If it's fine at every point, then
That classical.
so no, but you can use the same argument from Alberti, Bianchini, and Kripa. They assume that you're, I think it's actually Lipschitz, so you have a constant. And I think even for the covariate formula, you have to assume that this is true as well. But one thing that you can take advantage of for a function like this, which is for which this is bounded everywhere, you know that it has to be differentiable almost everywhere, just like a Lipschitz function or Rademacher's theorem. But you also know that it takes measure zero sets in its domain to measure zero sets in its codomain. And with this, and this is kind of very similar to what you're doing with the covariate formula, even for Lipschitz functions. So you take the set of, or you take the set of points in which are not differentiable, you take the set of points in which are derivative zero, and you can say that essentially you can't see them. Everywhere else you have something else. But I suppose, yeah, so I guess my answer is not exactly what I originally said. It's not really by the kind of very easy covariate formula or covariate formula argument from the ABC paper, but it's by the same kind of logic, essentially. Any other questions? Okay, yeah. Cool.
Do you know if your theorem is optimal? So could it be that it's differentiable almost everywhere, or
Oh yeah, no.
you have counterexample?
Yeah, actually, there's a counterexample, a very old counterexample in the dimension D=1 case from Veskovich, in which
So is there a canonical example we should have in mind?
very canonical.
A canonical example of such a function, wiki Lipschitz.
Let's see. Here, I'll give you kind of another characterization of these types of functions in the D=1 case. Okay. So, and in fact, I want to start the D=1 case for both examples, essentially, for the level set problem and for this problem as well. So what happens, and really, what this relies on is what happens in the one-dimensional case anyway, is that if you have some function, okay, and its little lip is small, but at all but kind of many points, and it's continuous. And so it satisfies this. Then the graph now let's say for all x, and the graph this is kind of what you want. Of course, maybe this is not a very good way of thinking about it. I mean, I'm not saying that you can break it up into countably many finite measured curves. I'm saying that you can break it up into countably many finite measure sets. So this is maybe not the best way to think about it, but this is maybe kind of what you're kind of dealing with to some extent.
Is that a characterization or an implication? Because you just you've drawn one arrow.
I did draw one arrow. Let's see, so let's see if my graph, No, I am pretty sure that you can come up with an example. She won't go through.
We should don't go, doesn't go the other way.
Pretty sure, actually. I don't know if I really talked about this, but yeah. Okay, so keeping with the one dimension, the question, obviously you don't care about maybe the geometry of the level sets, just the size. Okay, so the question is, given this type of regularity, can you say that our level sets are almost and we'll start with maybe a positive thing that one can say. So let's say you have F. Finite. X. Then yes, then almost every but this goes by exactly kind of the same argument that I was giving before in the higher dimensional case, essentially, that you have two conditions here that you're going to be differentiable almost everywhere, but you also know that if so you have these two things that you're dealing with. So either, and you look exactly when you're not finite, you either have a zero derivative or your derivative does not exist. Okay. All right, that's cool. And then of course you need to use the fact that the set of points in which your derivative is zero is going to be mapped to zero, and it's going to measure zero as well, unless you're constant. But okay. Okay, sounds good. Or sorry, the image of it is going to be zero. So yeah, so of course, I keep using this countable exceptional sets. What happens if you don't have a countable or exceptional set? What if you have a larger exceptional set? Uncountable breaks everything. Essentially, which if you have a continuous function, take a set of take an uncountable set to a set of any dimension. Essentially, this is the idea in the graph. So 2. Yeah. Maybe I should write this. I'll write this slightly different. Makes more sense to be accountable. So, continuous. this.
Okay.
Okay, but this is actually not so bad. Essentially, you say, okay, I have an uncountable set. I can give it a Cantor set type of representation. And then I build my function outside of that Cantor set. And make sure it's very nice. Okay, we'll do like some type of middle something Cantor set. Okay, so you start maybe here. And then you say, well, I just need something that eventually will be continuous and also whose images, let's say all of 0, 1. Right? So something like maybe something like this. And then you do the same thing. And over and over and over again. All right.
If you want to diminish the range each time, so
Yeah, sorry. Yeah, sorry. I'm doing it slightly different. I need this, right? And then this one.
So are we also assuming E has 0 measure?
It can have 0 measure, it can have
Out of dimension.
it could be very small. Yeah, I mean, they could have household dimension 0, of course. For positive measure, I suppose. I mean, it's more obvious, but yeah, the idea is if it's very small, but still uncountable. Yeah, and I suppose that's really all you need. Yeah. Okay, cool. So
I'm sorry, I didn't follow that argument. So in this case, E is,
yeah, E is covered by the nice Cantor set, yeah. And so of course you don't want it to the Cantor set to have anything other than E in it, but you can adapt the Cantor set to your setting. Okay, so it doesn't work for that case, and then of course you could ask for small lip. If your exceptional set is smaller, can you do the same thing? And the answer is no, and it's a typical answer from when Mariana and I work together is that if we think that something maybe is true, and then we end up with a counterexample. So I don't know, it's common for us, I suppose. Either way, so okay, so let's say make sure I'm not skipping anything. Yeah, okay. So for small. There exists so even without an exceptional set. And so essentially what you need to do is a kind of copy what we did here, but you have to be a little bit more careful, obviously. And the way you'd be more careful is just with a type of decomposition argument, essentially, which allows you to say that if you want to do this type of iterative argument, and the issue that comes to play, especially when you don't have an exceptional set to throw all of the worst behavior into, is, well, how do you deal with this, essentially this iterative type of construction? And so you have to do an iterative type of construction in which things far away, but not too far away, don't destroy the type of regularity that you want to maintain. Okay. And so how do you do something like this? Let's see. Let's say you are at some step in the, so you're doing an iterative construction, and you're at some step, and you have some interval here, and you want to keep your small lip relatively small, and so you want to make sure that you stay in this box at this scale. And so how do you do your construction? Well, you first you split your box into a small rectangle and a bigger rectangle, and then in the small rectangle you essentially want to do this type of construction. Okay? And in the bigger rectangle you want to do a Whitney decomposition, and do it in such a way, or and continue your construction in such a way such that you can do this same type of argument, and points relatively close to anything in this area don't affect others. So what do you do here? You do something fairly simple. You need it to, you want something like this, but it turns out maybe you want something like this, maybe a different color. Why do I need flat tops and bottoms? Well, I need to make sure that I get the infinite level set on these things, so it's not a big deal. It's basically the same thing as we did before. And then you break this up. Nothing incredibly crazy here. Essentially, you do the same construction inside of here, and the only thing that you really do worry about when you're trying to eliminate any exceptional sets is if you're near one of the edges of this construction, you don't want to lose the boundedness of your regularity. And so what happens is, of course, if you're near here, you just take a bigger box. And because of this type of dyadic decomposition, you know that you can rescale it by some factor, and then everything here is still in a certain box or a certain eccentricity. That's basically it. That's the whole argument, essentially. Okay. And you do the same thing over and over and over. There's some things that I'm oversimplifying it, of course, but this is the idea. And so it doesn't work in the one-dimensional case, and you can imagine it doesn't work in the higher dimensional case as well. But I think we're still trying to understand to what extent it doesn't work. We can create, and so I can say this in words before I describe the actual result and maybe draw some pictures. But when we go through this construction, we'll be able to construct a function that has a small lip property everywhere. It's continuous. Its level sets are not rectifiable, but of course they're not going to be purely unrectifiable. Okay, and so you're going to have a lot of rectifiability in these level sets, but I don't know, is that interesting? That's the question, or to what extent, how much of it is rectifiable versus how much of it is not rectifiable. This is that's still a question that we're considering. Okay, so I should probably get on with it. See here. So, okay. This is 21, I suppose. Here it is. This- And I suppose, I guess this is the point at which you wonder whether what you can do works in other higher codomain, higher dimensional codomains. It does, but with a very kind of basic extension. So but I'll give the construction to just the one-dimensional codomain case. There exists this. And rectifiable. Overall. Again, it's a little similar, but of course things are a little bit more complicated in higher dimensions. And fighting this or doing the same type of argument that I've erased already, but this it's not in the big lip case with an exceptional set that you want to cover essentially at every step of your iteration. You want to cover the codomain essentially, right? A little bit. You need to play some games in the two-dimensional and higher case in order to ensure you have the regularity that you desire. Okay, so two-step. Let's see. First up. Okay, I'm gonna attempt to draw pictures, but it's going to be a little bit difficult. Okay, so let's consider. So n is going to be some big fixed number. And at the step of your iteration, you're going to have, let's see for the moment, we have a cube, but in the cube in the domain. And in fact, I'll just do 2. The first is you play a kind of a common game that you play in analysis, I guess, is when you break the things into teams. Essentially, you decompose this and break it into essentially teams, so that one the behavior at one part of your board does not affect the behavior of the other. So you break it up into roughly, not exactly n squared but not exactly. Okay, you do something like this. Something like this. All right, and so of course you need some space in order to connect these things continuously. All right, and then you of course label things. So one, 2, 2, 2, 3, 4, two fours next to each other. I did not want that, but okay, it's, I think we'll be okay with that. And I also wanted 16 boxes, so I failed at that as well. So we have something like this, okay? And then we map F to different heights based on the number. Okay, so we say F of Q sub F of I is going to be mapped to something like let's see, I times into the minus K plus 1 or something like this, plus some linear function. Affine function. Probably a better way to describe it. No, actually, I think I want it to be like, that's fine. Plus some linear
And
function.
what is K?
K is the step, so sorry. So
Like in the big iteration.
yeah, the iteration step, so at iteration step, yeah, that's a very step.
Maybe you repeat how you assign the teams.
So essentially what I would like to do is assign them so that, and I did a very, very poor job here. I assigned them so that if you, and yeah, I was going to give a kind of maybe a combinatorial way of describing it, but I think I'll describe it in the way that I actually want it to be described. So what I want to do is create a sequence of Cantor sets that are purely rectifiable, right? And so if I had 16 there, I would essentially break this up into teams so that I would have different variations of like essentially a random Cantor set, but a random Cantor set that's actually purely rectifiable. Okay. And so I need to define these so that, and one way you can do this is say if you did have 4, if you had 16, you would put one box in each row such that they don't share the same column. Okay. This is one way to ensure that you'll have something purely rectifiable if you do an iteration process. And this is the way you construct the unrectifiable part or the purely rectifiable part in your level sets.
Linear function. What's its function is?
Yeah, of course. So
this number n is fixed over all iterations. Right?
yeah, the number in this fixed, yeah. So in these cubes, and now I want to write them not in 0, 1, 2, but let's say 0, 1, 3. Okay. I want above one of these cubes, let's say, and let's see if I can draw this even reasonably good. Say this is 2. The bottom of it is 2. Not exactly, of course, it's going to be above above 0, I suppose, or above the domain. But what I want here is something like this. So this is the linear function that I'm considering. And of course, what I would like, of course, is that when you project it this way, you get all of this segment here, so that you cover all of 0.
It's m to the power.
Yeah, and of course, yes, you want these essentially. How should I say this? So at different places. 2 as well, you're gonna have the same thing. And then at maybe a 3, or maybe a 1, excuse me. Slightly below, let's say. Okay, I don't know if this is giving a very good idea, but your domain here is here, 0, and we'll say this is yes, yes, we'll say this is at or actually I want this to be maybe some number, some alpha times into the minus k. It's alpha plus 1. I want something like this. And then some of my lower boxes are going to be lower, and then my higher boxes are going to be higher. So and I'm trying to draw something in 3 dimensions, but of course it can only go so far here. But some of the boxes are going to be a little bit lower, and some of them are a little bit higher.
Do I get the right idea that you just like take the function of like x, then just subdivide it, scramble all the pieces, subdivide all the smaller pieces, scramble.
Exactly. Yeah, and scramble them in such a way so that the level sets essentially construct the Cantor set, unrectifiable Cantor set. Yeah. And so, of course, you connect the things, but of course, even in these connections, after all these iterations, you're not going to see really the boxes that I'm constructing here, right? You're going to see the connecting parts between the boxes, right? The level sets. Okay. Yeah, so this is going to be like a rectilinear. Inside the unmarked boxes.
And at each iteration, you just repeat this in.
Yeah, and so you need to do another step as well. Actually, for the same reason that we needed to do this for the one-dimensional case, we have to do a Whitney decomposition for each of these cubes. Okay. So that we, at the edges, we don't get something we don't like, essentially.
And you don't have to be careful with the rectilinear extension because you've already messed everything up enough at that point.
Yeah, and it's after that it's also fixed and everything like this.
So in the iteration, what is happening actually outside of those cubes that you label, that's fixed.
It's fixed.
You're not going to touch. You're only going to modify the label cubes.
Exactly. Yep. Okay. Yeah, and so and of course you do some type of the same thing you had here, but of course now this is going to get pretty ugly. But that boxes here and then smaller boxes as you get closer to the edges, and then you repeat. Yeah. So I don't know. I think this is kind of fun. It's kind of cute. I enjoyed working on this, and that's also we could talk to a graduate student about as well. So it's pretty nice. I think that Igra's was second year or something. So it's pretty nice to talk to. And yeah, in case she came up with a lot of good ideas, which is really cool as well. So yeah, I mean, there were questions. Of course, after the level sets, right? You're gonna have maybe. And I'll write it in maybe like the nicest possible cases when you actually have maybe a 4-corner Cantor set, let's say, at some level sets. But generally speaking, it's going to be actually a little more random than this. But you're going to see every iteration essentially, right? These are going to be hollow, essentially, boxes, and you're going to see every iteration to the end. But that means you have lots of rectifiable pieces, very, very nice rectifiable pieces, in fact. And actually very little, relatively very little unrectifiable piece, which is not something that we thought about too much, but it could be. Yeah, I don't know, I think this is. Yeah, I think, on this, I think this is more or less what I would like to say. I mean, I think we can still maybe talk about, or one could try to understand what happens for the connected pieces and not the pure unrectifiable pieces of these things. But this is kind of maybe the first step. Something hopefully, hopefully more interesting. So I'll finish there and stop. Thank you.
Questions?
Well, so, I mean, is this supposed to show us that that's really not a very good definition?
Yeah, so it's not going to give you a nice. It's not going to give you very nice properties of your level sets, and so although this assumption does tell you that you're going to be differentiable on a set of positive measure, positive big measure, you can say almost nothing about the level sets. And part of this kind of, I guess, this journey that we were taking essentially is we did not completely understand what this set of differentiability for these functions looked like, or what we could say about them. And so this could have been a way to maybe understand them a little bit more to some extent. Of course, we got to a counterexample, so we have to go back to the drawing board, but yeah.
Well, but I mean, if you have a counterexample, then you want to have a definition that you can work with.
Yeah.
Do you have any idea what that should be?
Well, I think, and I would imagine that essentially, and I suppose this is actually maybe to some extent answered by what we talked about for the local Lipschitz condition with the exceptional set, is that Lipschitzness everywhere, or Lipschitzness, excuse me, everywhere but a countable set is really the thing, and maybe possibly the weakest thing you can say to ensure that almost all of your level sets are nice. Yeah.
What if you play with, like, take the oscillation divided by R and say that it is integrable or something like that?
Yeah. So this is, in fact, the reason that we started looking at this is that Chenya and Volog, they had looked at essentially this type of regularity for this small lip constant. They looked at integrable regularity and some type of course like solo embedding. If you can assume that you have some type of integrability, and so you can say fairly nice things there. And in fact, I suppose, if you want to say something similar to what you have here, but even I suppose something similar to what Alberti, Bianchi, and Kripa talk about, you can assume a level of regularity or integrability for your little lip constant. You can do some type of embedding and get to maybe something like W21 or something like this. And then from there, you can say the level sets are actually fairly nice. And in fact, even more than just rectifiable, but you could say you have this kind of parameterization by Lipschitz curves. But I mean, this just follows. This would just follow basically immediately from what they've done before.
So there's this very strong connection between like level sets and oscillatory integral estimates. When you have, your f would be the phase function. So do some of the examples that you have here, or the construction that you've shown, give you some kind of oscillatory integral estimates that are not as good, like exhibit some, suboptimal decay, something like that?
I know, I don't know. But yeah, I don't know actually. That's a good question, but I have no. Thank you very much.
So in your example, do I understand correctly that your level sets are still one-dimensional though, even though they are unspecifiable? Is there anything which looks like the characterization that you gave, well, the property that you gave at the beginning? You know, if this little L is bounded and it's your one-dimensional domain actually, so your graph has sigma finite, it's H1 sigma finite. Is there anything like that in higher dimension that one could possibly?
I see. So no. So one of the things, so actually, let me try to think for a second here. No, so you can. Yes, I believe you can say something like sigma finite, but then one of the things you. All right. So when you're going from this type of understanding of the length to some extent of the set, or let's say a connected set or a graph of a function to its regularity, then of course when you go to higher dimension, everything falls apart, right? Because if you have, I mean, the easy example, of course, if you have a finite length curve, it's differentiable almost everywhere, but if you have a finite length or finite surface measure, a surface, it could be and non-differentiable everywhere. So yes, the characterization exists in that sense, but we never used it because it's less useful for regularity.
But it still would be the case, for instance, that this little LF finite implies that the HD dimensional, that the graph is HD sigma finite. That's what you're saying.
Yeah,
Is that correct?
Yes.
It's just, well, of course, I mean, it's not something that, I mean, it's a W1P function with a sufficiently high P, like for instance, we have that property for the maps from R P to RP. So. Okay, there does not seem to be any other questions, so thanks.
Sure.